Okay. In the last lecture, we covered the acceleration analysis, inertia representation, and the Newton-Euler formulation of robot dynamics. In this lecture, we will cover the alternative formulation, Euler-Lagrange formulation of dynamics. Now, the Euler-Lagrange working rule is uh, something that hits the uninitiated um, as out of the blue. So I would first spend a significant amount of time, almost half the lecture of this, almost half of this lecture, to um, connect Newton's laws, which you believe in, to the Lagrangian dynamics formulation, and then use it for the dynamic formulation of robot manipulators. And what we are covering now applies to not only robots, but all systems of rigid bodies. Okay. So the robot has several links, each a rigid body, because we are talking about rigid link robots. And each of those rigid bodies is composed of millions and millions of particles held together by the rigidity of the body, right? So all those millions and millions of particles of all those bodies, suppose there are capital N of those particles, very large number. Okay. So each of those particles can move in three directions, say X, Y, and Z. So there are 3 times N motion coordinates of all these particles. Now, in these motion coordinates, there are constraints. Some because of the rigidity of one body, and some because of rigid connection between two bodies. So those constraints typically operate like this. There is an equation among the coordinates of this point and that point, which ensure that the body as rigid remains rigid. Different points of the same body do not change the distance between them. And if there are connections between two rigid bodies where relative motion is not allowed, so that relative motion equal to 0 is ensured. And now these constraints are maintained by constraint forces between two particles of the same body or two particles of different bodies, whatever. Fine. So these constraint forces stop the relative motions which are not allowed by the constraints. That is how it is not allowed. Now, how many such constraints are there? There are 3n minus k, where k is the number of degrees of freedom of the system. So if you are talking about 6 degree of freedom system, then among the 3n motion coordinates, there will be 3n minus 6 constraints. So the remaining 6 variables will be free, and in that motion will be possible. Okay. So those are the relative motions which are possible, where such constraints do not apply. So we talk about generalized coordinates. K coordinates of the entire system we choose in such a manner that in terms of those k coordinates, x are all the other original motion coordinates can be expressed like this. Okay. Because of these constraints. So there are 3n minus k equations among 3n unknowns. So leaving aside k of the k unknowns free, in terms of them, all of these can be expressed. So you can reorganize these constraints in this manner. Okay. Such Qs you select. And these are the minimal set of coordinates which can describe the configuration of the entire system satisfying these constraints. The rates of these generalized coordinates are known as generalized velocities. And now, if there are changes in these q's, delta q1, delta q2, etc., corresponding changes in xr are given like this. Delta xr will be del xr by del qs into delta qs. So contributions of all the changes will be summed up together over S. Now Newton's law says, now from here we start from Newton's law and connect finally up to the Lagrangian formulation. Newton's law says mr into xr double dot, that is mass of that little particle, rth little particle in and into the second derivative of its position coordinate is equal to total forces on them. So all the forces on this particle that are active are summed up together here in Fr, and the constraint forces are summed up together here. Constraint forces which do no work because they come into play to stop relative motion and through which a work would be possible, and therefore constraint forces do not contribute to the work. So now what we do is that we impose that condition mathematically. Constraint forces into delta xr summed up over r is 0. Fine. Now we multiply this with delta xr, sum up over all r on both sides. On this side, this part will have no contribution, only this part will have contribution. So we get this sigma r mr xr double dot into delta xr is equal to just fr delta xr summed over r. This part will make no contribution because of this, their nature. Now, both sides, if you divide by delta qs and then take the limit as delta qs tends to 0, then here you will get the partial derivative, and here also you will get the partial derivative. This would be delta qs, not delta s. Okay, this will be delta qs. Now, this quantity is called the Sth generalized force, Fr times del xr by del qs, because these are the forces corresponding to the generalized coordinates. Okay. Now, depending upon whatever coordinate that generalized coordinate is, position, angle, or something else, the quantity here will turn out to be force, moment, or appropriate something else. So that the generalized force into generalized coordinate, the product matches the dimension of work and energy. So in that sense, it is generalized force. Now this generalized force, now here the derivative is with respect to delta qs. So the Ss generalized force is this, which can have two components. One is the conservative component and the other is non-conservative component. Now we separate it out because of an intention, which will come in due course. Before looking at the right side of this equation, we process the left side a little. This is the major analytical processing. Okay, so we first simplify this and equate this to something else which will be in more appropriate form for our purpose, and then we will take up this side. So take the left side for the time being, this left side. Now in the first step, what we have here is mr xr double dot del xr by del qs. Now we want to remove one dot from here and put a d by dt here. Is it okay? It's not exactly okay, because d by dt of this whole thing will mean the derivative of this entire product. This sigma is creating no problem, because derivative of a sum is the sum of the derivatives of individual parts. The sigma is creating no problem. Problem is here. The derivative of mr xr single dot into this will be derivative of mr xr dot into this, which is here, plus mr xr dot into derivative of this. That will be the extra term. So what we do? We do that replacement, take one dot away from here and put d by dt here, and whatever is the extra component, that we subtract. Okay. So in this derivative, mr is constant anyway. So in this derivative, we have derivative of this, which is here, into this, which is here. The first part of the derivative takes care of the entire left hand side. The second part, which is mr xr dot times derivative of this, that we subtract to maintain the equation. Okay. Now, from this step to this step, we have done two things. In this term, del xr by del qs, we have replaced with del xr dot by del qs dot. You see one here in green. Here, in place of d by dt of this, we have put del by del qs of xr dot. So here, the partial derivative is first, and then the time derivative takes place. Here, over xr, the time derivative is first, and then the time derivative is partially differentiated. So these two justifications are here. One. First of all, what is xr dot? Since xr is a function of q1, q2, q3, q4, etc. and t, therefore its derivative is the total derivative, that is del xr by del q1 into q1 dot plus del xr by del q2 into q2 dot, and so on, plus finally del xr by del t. So this is straight from the definition of total differentiation. Now consider this as an expression and differentiate this partially with respect to del qs dot. So qs dot a partial derivative. Okay. So qs dot appears only here in a linear fashion with this coefficient del xr by del qs. So in this entire sum, q1 dot appears once with del xr by del q1, q2 dot appears once with del xr by del q2, and so on. So the partial derivative with respect to xr with respect to qs dot will be just this coefficient. So partial derivative with respect to qs dot is just this coefficient, and this coefficient is this. And that is why in place of del xr by del qs, if we are writing del xr dot by del qs dot, there is nothing wrong. So this is correct. Now the second one, this one. Okay. The way we talked about differentiation of xr dot, like that you can talk about differentiation of this, time differentiation of this. Okay. Here we were talking about differentiation of xr dot with respect to this. Now here we are talking about differentiation of this partial derivative with respect to time. Again, xr is a function of q1, q2, etc. and t. So del xr by del qs is also a function of those things. And the total derivative of that with respect to time will be derivative of this with respect to q1 into q1 dot plus derivative of this with respect to q2 into q2 dot, and so on. That is here. Derivative of this with respect to q1 into q1 dot plus derivative of this with respect to q2 into q2 dot, and so on, plus finally partial derivative of this with respect to time. Again, total differentiation formula. So we have got this. Now from here to here, here it was del by del QU of del XR by del QS. Here it has been replaced with del by del QS into del XR by del QU. Since QU and QS are two independent coordinates, so we know that del 2f by del x del y is the same as del 2f by del y del x. Okay, so this replacement is correct. Everything else is as it is. Okay. Here also we have done the same thing. Replaced QS and T, interchanged them. Through this maneuver, what has happened is that the common differentiator QS has come outside in both terms, and the different ones QU and T have gone inside, and therefore this sum now can be put together as del by del QS of this whole thing into this like this. Okay, and then this whole thing is by definition xr dot, and therefore this is del xr dot by del qs. So here this interchange of time and qs in differentiation is all right, right? From here to here. Here it was derivative with respect to qs first, then derivative with respect to time. That is, position was differentiated with respect to generalized coordinate, which was then differentiated with respect to time. Now here directly first differentiated here velocity, and then the velocity is differentiated with respect to this. So this is also fine. Now we have got this. And now notice, at this stage, the differentiation will have no problem. First of all, this mr xr dot del xr dot by del qs dot. So what we have done here is that del by del qs dot we have taken outside, and inside we have put the integral of this. Okay, the half mr xr dot square. Verify this. If you try to differentiate it with respect to qs dot, then what you will get? You will get half mr into twice xr dot, so that twice will cut this, and xr dot is appearing here, into del xr dot by del qs dot, which is here anyway. Fine. Similarly, this term is the derivative of the same half mr xr dot square with respect to qs. This one was with respect to qs dot. Okay. So now if you take this sigma r inside the way it has been taken in this term anyway, then you can recognize the kinetic energy here. Okay. Half mr xr dot square summed up over all the motion coordinates r is the kinetic energy of the entire system. Here also take this sigma inside and you will get the same kinetic energy. So that is here, right? So this whole thing comes down to d by dt of del by del qs dot of kinetic energy minus del by del qs of kinetic energy. So this left side has been reduced to this with the definition of kinetic energy as we know. Now take up the right side. Right side has a conservative component of a force and a non-conservative force. Now, the conservative component of a force is derivable from an appropriate potential energy. That is what makes it conservative. Okay, so QS conservative part is the minus equal to the negative of del V by del QS, where V is a function of Q, potential energy, only position, no velocities. Okay. So potential energy is the energy of the body or system that is possessed due to its position. Okay. And therefore, del V by del QS dot will be 0 because it does not depend upon velocities. And then the left hand side we reduce to this, the right hand side, which was this thing plus QS, the non-conservative part. So in place of the conservative part, we put this. And then if we take it on this side, then here we will have del by del QS T minus V. Okay. And here d by dt del by del QS dot, here also you can say T minus V, because what we would be including minus del V by del QS dot, which is 0 anyway. So we put them together and we have got this. Now this T minus V, kinetic energy minus potential energy, is the Lagrangian, which is the key element in Lagrangian formulation. So this is a Lagrangian function. And this is the dynamic equation. Okay. In vector form, this partial derivative with respect to QS dot, scalar one component QS dot, will be replaced with the gradient, that is vector Q dot. And similarly here, this will be the partial gradient with respect to positions. And this will be the vector of all these generalized forces. How many of them? K of them. So this is the Euler-Lagrange dynamic equation, and the way to get the actual equations is to construct the kinetic energy, the potential energy, take the difference, call it Lagrangian, and then conduct all these differentiations, and that would produce a huge expression on this side in terms of all the QS's, all the QS dots, and all the QS double dots. And that is equal to the generalized forces, which may be force moment depending upon what is the corresponding coordinate. And this is the dynamic equation. This is a vector form which has k scalar components like this. Okay. Now the way we connected this with the Newton's laws, you can also connect them with an alternative formulation of dynamics, which is Hamilton's principle of least action. In fact, physicists are very, enthusiastic about this. This Hamilton's principle they consider as something very fundamental, and from that you can derive this, and you can derive even Newton's law. So rather than calling Newton's law as law, you could theoretically call this as the law, this principle, and derive Newton's law as an outcome, as a consequence of that. They are equivalent. Okay. So what this principle of least action by Hamilton say? It says evolution of a dynamic system from one configuration Q1 at time t1 to another configuration Q2 at time t2 takes place along a trajectory over which the action, which is the integral of the Lagrangian with the initial point bound to Q1 and final point bound to Q2 at times t1 and t2, is a minimum. And if it is a minimum, then it has to be stationary point. That is, first order change has to be 0. First order change with respect to what? That is, if the change from Q1 to Q2 is taking place along a trajectory, really, then any little variation along that trajectory would change this stationary. So, when you apply the first order relation, that in place of Q dot, at such a time, if you take a little different trajectory, you consider Q of time and Q dot plus Q dot over time, then the change in the Lagrangian function will be this. And the stationary action basically means that the integral of this change is there are two points here. This and very little at all time, except that at time t1 it is 0 because this is given, and at time t2 it is 0. Besides, the partial changes in delta q and delta q dot, partial change in positions and velocities, the explanation of delta velocities should be such that the time derivative of delta q is equal to delta q dot. So there are consistent variations. That is, some delta q and whatever else delta q dot will not work. K of theta zero. What is the idea? Positions velocities. S what of the Lagrangian? And once you have what of the Lagrangian, if it is over, then it's not Lagrangian function with respect to the highest velocity. Partially, the partial derivative for the differential which is defined for the integral derivative. From that, subtract the partial derivative with respect to the position. So the force that is the third dot joint. There is a here, one, there is a 3 dot here, and then d by dt of this. And this d by dt will be one lot of differentiations because this is a function of k on the function of time eventually. They have to be differentiated, and then the corresponding time derivative of that thing we have to verify with the example. Now, how do I look like? This is generally we see a particular example, but this is what gives you the overall sense. You see, finally, the velocity of its center of mass is a linear transformation from the velocities. That is a matrix Ki into theta. So this matrix Ki will be 3 by n. Well, this is n vector. But we have its velocity in the 3 matrices. Similarly, would be another similar matrix Vi times the n vector. So final energy of the body, I think, will be half mi vi mod square, which is the vi, plus half omega I transpose on inertia omega I. This is the final energy of the motion. When you put this vi and this omega I here, then here you get half theta transpose from here, mi vi transpose vi theta. This vi here, and this first theta transpose is going to be this vi transpose here. This theta, so we have to plus half. Here also you put this theta transpose vi transpose ci I vi theta. So theta transpose you take on this side, theta transpose the transpose is and theta you on this side, you have this. Here you have a matrix. Here you have another matrix because everything ci is a matrix. You multiply on vi by vi on this side and vi transpose on this side, means here ai is a matrix. Doesn't matter because ai transpose ai is a matrix. Mi is scalar, so this is symmetric. And on this side outside half theta transpose, and on this side theta here also same thing, transpose. So these two theta transpose here is one symmetric matrix now, and ai size or mi size can be there for the board. With different ai and bi of course by seven. So that's half theta transpose. All these values are equal to 1 to 6 or whatever it is. This matrix is a measure matrix. And now we've got A. One of the key steps here. This one. Now here I am saying that represents suddenly here is K. And here is independent of this. And this is partial differentiation. And add all those, then you get this vector. And you see half theta transpose m theta. This is independent of theta dot. So you get half m theta, but half twice because once this part is differentiated, once this part is differentiated, both of them will be transferred together, and when you add up the two, m theta dot. I simply derivative of this m theta dot. So m theta dot and differentiated. And this is complicated because it will be m into theta dot plus d by dt into theta dot. M theta dot plus d by dt into theta dot. This d by dt, m is now this is a function. So this m is function of theta only, and therefore it will be derivative of theta that entire. So here now this is a transfer. Basically what's happening here is m is a matrix function of variable. So when you check this, you get this thing which is n by n derivative. So what it means is in this equation, k component will have derivative equal to theta k dot here, and k component of this matrix product, and here so each component of this equation will have derivative equal to that particular derivative is future. And this is by theta dot. Now also this is by theta. That will have both components. The k by theta minus the d by theta. The k by theta is here. Now this partial so you give this side, this is this. And then you get inside which is same thing here. It comes with half here. Then by theta, this component is here minus the d by theta. You get function of theta and you take the and you take the derivatives, you get function of theta or function you get y g theta. Now this equation this is by theta and this equation this is by theta. You get the equation. This minus this equal to the non-conservative force cube. So that is this minus this. So this comes is from here, this thing, and here is half. Let's subtract half units. So half is minus plus d. That means this is the equation, which is rest. Forces as this equation. So these two things. Part is this side is equal to this side. Now you take this equation on the other side. You get the equation. That is this, then this, then this, this equation on this side. So this is the system of equations. Here you have the initial term. Here you have the secondary terms. Basically, this is a quadratic expression of all the theta dots. Now in which some of the terms will be theta I dot square. These are typically the central components, and some terms will be theta I dot theta. Theta I dot theta dot. They will be the polynomial components. Actually, there is possibility of one more term, which we saw in the static force transformation. I've got Rm. Then the Rm vector with the data force transformation. Is the corresponding in the first side. So the data force the force reduction formula of the vector with the environment is in the equation. So this one in dynamics talk about understand problems that we need to solve and how the equations are applied in solving those problems in application, and how this part one particular will become to and you'll find that in part of the example the calculations are quite handful.